it working? Yeah, I think it's working, right? Yeah. So as you can see, I'll be talking about neutrinos. Just to get a sense of the audience, I'd like to see how many people have heard about neutrinos before. Good. All right. What about things like quantum mechanics? Have you heard about that? What about the superposition principle? Some piece. All right. And what about the Higgs boson? Excellent. All right. So Pierre is very sophisticated, and I think he's quite right. So I'm going to start off a little bit unconventionally and ask you to consider, suppose I have a chair, okay? And I tell you that the chair doesn't have arms, okay, you say? And nor does it have a back. And you say, okay, maybe that's more like a stool than a chair, but fine. Doesn't have legs, and doesn't even have a seat, okay? And so somewhere along this line of thought, you probably said, you probably don't have anything at all, right? And then you might wonder, oh, well, is this some kind of pathetic attempt at humor? Am I trying to make some kind of analogy or a metaphor? And yeah, why are we talking about chairs? So let me come more to the point and say, I tell you that I have a thing called a particle. And usually sometimes we think of particles as having things like electric charge that allow us to interact with it and detect it. But this particle doesn't have electric charge. And in fact, it doesn't have any properties that really allow us to readily see it in any form. So much so that it can actually easily penetrate 10 billion meters of lead without leaving a trace typically. Sometimes you'll interact, but sometimes, most of the times it won't. It may also have no mass, so you put it on the scale and it doesn't weigh anything. And so similarly, you wonder if there's anything at all to this particle, right? And does it make sense to say that such a thing exists? And yet, we know that this particle, which you might guess is a neutrino, it's a fundamental building block of the universe. It's a critical element in understanding the nature of other particles.
There's an LED as well as
I see, yeah, thank you. And it's produced copiously by both natural sources, like the sun or the supernova, exploding stars, and also artificial things like nuclear reactors. And there's so many neutrinos, in fact, that you may have heard that just from the neutrinos from the sun, there are millions of them streaming through every square centimeter of the Earth every second. And then when a star explodes, actually 99% of its energy is released in neutrinos rather than light. And as a result of this abundance, it actually plays an essential role in the evolution of the universe. And things like the stellar astrophysical processes which let stars burn. And also possibly why the universe exists at all. And so that's what I'd like to talk about today. And before I get there, I'd like to explain the title a little bit. So if we go back to the 1920s and 30s, so this is when all the big things in quantum mechanics and special relativity were happening, and all the names you recognize like Albert Einstein or Marie Curie, Werner Heisenberg, Fermi were all in action. And by the 1930s, a very simple picture arose about what matter actually is. And basically, there were just two components to it, the proton and the electron. Okay? And so when we think about an atom, all it was some protons bound together with additional electrons inside, and then some electrons orbiting outside, which basically determine its chemical properties. And so that was a very beautiful and simple picture. But there were a few unresolved issues by the time sort of 1930 rolled around. And this was called one of them was called the spin crisis. I don't know what the other one, I just call it the energy crisis because there's something similar. So there's a process which a nucleus can undergo, which is called beta decay. And in this process, basically a nucleus will disintegrate into another nucleus and also emit an electron at the same time. And so the considerations of energy and momentum conservation, they basically say that these things have to come out back to back with a fixed energy. Okay? And so we can predict very easily what the energy of this electron or the recalled nucleus should be. But as it turns out, this electron is observed to have some kind of spectrum, right? It's not just one fixed energy, but a broad range of them. And they just couldn't really explain this. And so much so that Niels Bohr said that maybe energy conservation just doesn't work in this new world of quantum mechanics and the nucleus. Okay, so that's beta decay, or the energy crisis. The spin crisis is a little bit more subtle. And basically, it's a statement that this Rutherford model doesn't add up. And so what we can do is take a look at the nucleus, and it actually is spinning. And the spin it has is actually related to how many things are inside. And such that if you have an odd number of things inside, then you have a certain sequence of spins which are what we call half integer. Things like 1/2, 3 halves, 5 halves, and so on and so forth. If there are even number of things inside, then the spins are integers, 0, 1, 2, 3, 4, and 5, so on and so forth. And so the nitrogen atom, or the nitrogen nucleus, according to the Rutherford model, has 14 protons inside it and 7 electrons. So it should have it has an odd number of particles, 21, so it should have sort of one of these half-integer spins. But as it turns out, it has an integer spin. And so that was sort of another mystery. And so what the desperate remedy was in fact conjecture by this gentleman here, Wolfgang Pauli, which he famously actually submitted within a letter, which is an excerpt of it, which is here. And you can see it says, "Dear radioactive ladies and gentlemen." So he addressed himself as already made it of some notoriety. And then he basically said that with his, his desperate remedy is that there's actually a new particle in the nucleus, which he calls the neutron. And that particle is also emitted with the electron and the other nucleus when we undergo beta decay. And as a result of that, this sort of fixed configuration of energy doesn't exist when you have 3 particles. And likewise, now, if you consider the nitrogen nucleus, it's actually 7 protons and 7 neutrons. And so now we have an even number of particles, and that's why it has an integer spin. Okay? And so he said, I can solve both of these problems with my desperate remedy. As it turns out, it was a little bit more complicated than Pauli thought. There were actually 2 new particles involved. The first is a neutron, which is actually, as we know now, bound within the nucleus with protons. And that solves the spin statistics problem. But a different particle, which we call the neutrino, is emitted in beta decay. And so it was actually Enrico Fermi, the gentleman over here, who made this additional addendum to Pauli's original hypothesis. And so there were actually 2 particles, each of which solve one part of this mystery. So now there was a problem here because, Pauli's saying that there's this new particle. Let's focus on a particle called the neutron, another one called the neutrino. The neutron is actually very quickly found within a couple of years by James Chadwick in Britain. But then, as far as the neutrino is concerned, people knew enough about quantum mechanics that they could sort of predict some of the properties of this particle. And they came to the same conclusion that I opened up with, that a neutrino at this energy can travel something like 10 to the 15 kilometers without interacting. And so within this same paper by Hans Bethe and Rudolf Pyros, they said there is no practically possible way of observing the neutrino. But they said that, yeah, we'll never see it. And to which Pauli responded, I have done a terrible thing. I have postulated a particle that cannot be detected. So this sort of comes back to where we started off, right? That here's this thing which is basically trying to explain some accounting issues with energy conservation, but somehow we will never actually directly see its presence. And can we actually, does it even make sense to say that such a thing exists, or is there something more deeply going on? Well, as it turns out, at the time it was impossible to see, but if you imagine between 1930 and 1940, a number of things happened. We won't go into that, but we did start into the nuclear age, and with the advent of nuclear reactors, which could crank out something like 10 to the 20 neutrinos per second, the neutrino was finally discovered by gentlemen Friedrich Reines and Clyde Cowan, who won the Nobel Prize in 1993, actually along with Martin Pearl, who was at SLAC at the same time, for something different. And so he sent a telegram to Wolfgang Pauli, and at the time, Wolfgang Pauli was very happy to hear this news, and he opened up a bottle of champagne. Interestingly enough, Reines went back to those authors of the other papers and say, you said that this can never be done, and what do you say? What do you have to say for yourselves now? And then Bethe, very, very kindly just said, well, you shouldn't believe everything you read in papers. Yeah. Now, this was actually how the neutrino was discovered with nuclear reactors. But in fact, there's another option to do this, which came from the nuclear age. And the original proposal was actually to use a nuclear bomb. And so this is actually from Reines's Nobel lecture. And so you can see he's going up for the challenge. So why did we want to detect a free neutrino? Because everyone said you couldn't do it. Not very sensible, but we were attracted by the challenge. After all, we had a bomb which constituted an excellent intense neutrino source, so maybe we had an edge on others. Well, okay, we won't worry about that. But they actually conceived of a proposal for this experiment. And it basically says, I'm going to have a detector over here. When I say go, you let that nuclear bomb go off, and I'll tell you if I see any neutrinos. And as you can see here, this experiment was actually approved by the authorities of Los Alamos, was superseded by the approach which used the fission reactor, which is the one over here. And so it's interesting to see that back then, the understanding of this nuclear physics was considered so important, and the understanding of these neutrinos and what role they had was so important that basically the military was ready to set off a couple of nuclear bombs to see whether they're there. But people were clever enough to find a different way. So this property of the neutrinos being so weakly interacting actually poses an extreme issue in trying to study them, as you can imagine. So this is the first piece of mathematics here that I'll put up. And it's what I call sort of neutrino economics. How many neutrinos can you actually observe? And yeah, there are some fancy figures here, but it's actually pretty simple. So this number over here, the sigma, is basically just a property expressing how weakly the neutrino can interact and how rare it is. And so that very, very small number can be overcome if you have lots of neutrinos. That's what this thing over here, that's basically what we call the flux of neutrinos. How intense is your source of neutrinos? And this here, the V, as you can imagine, stands for volume, N is density, and epsilon is the efficiency. And basically what these three products say is you need a detector that's very, very big, very, very dense, and then also you need to be able to see that a neutrino can actually interact. It's not enough just to have lots of material, right? You have to actually know that a neutrino interacted with it. And as a result of this, there's some really ingenious experiments that have occurred with which we study neutrinos. And so things like the Antarctic ice and the ice cube experiment have been employed as a neutrino detector, as well as the Mediterranean Sea. There are enormous underground caverns where we place things like liquid simulators, kilotons of them, to detect neutrinos. Iron plates from World War II battleships are recycled to make neutrino detectors. And so you can see that, yeah, people have really been ingenious about how to overcome this incredible superlative shyness of the neutrino in order to make discoveries. And so you can get a sense of the size of these experiments. Here's a detector made of water. There's a person on a boat. And then that's the Eiffel Tower for comparison with the ice cube detector. So in terms of the neutrinos, what we've learned since then is that neutrinos come in three species, or what we call flavors. And it's actually pretty simple. Basically, when a neutrino interacts, it will produce another particle. And basically, we categorize the neutrino based on what particle gets produced. And there are these three particles, one of which we are probably familiar with, which is the electron. But then there are the additional two particles called the mu and the tau which was actually discovered here at SLAC. And so when these other neutrinos interact, they actually produce this muon or tau particle. Okay? So that gives you three species, depending on what particle gets produced when the neutrino interacts. There's also, neutrinos also have antiparticle partners, which we call antineutrinos, and they produce the corresponding antiparticles relative to these particles over here. And so you can see the charge switches sign because we're now generating antiparticles. Now, there's a further twist to this, which is that you can see, we said that there are three kinds of neutrinos that depending on how they interact. But neutrinos, as we know now, also have mass. And so we can also label the neutrinos by which mass they have. And so you might think that those would be the same thing, right? The electron neutrino weighs so much, the muon neutrino weighs so much, and the nu tau neutrino weighs something different. But actually, quantum mechanics says that they don't have to be the same. And so what we call the electron neutrino can actually be some combination of these three different mass neutrinos. And likewise, the muon neutrino will be some different other combination, and likewise the tau neutrino. And so, okay, so this is probably the most math we'll see for today. So what this allows is a neutrino that is created as one species, let's say an electron neutrino, to be detected as a different species after traversing some distance. And so these things are, this is basically the probability. And what you see is that this is related to the mass of the neutrinos and the distance that it travels. And as it turns out, another challenge that nature has thrown at us is that in order to study this transmutation process, the neutrinos that we produce typically have to traverse something like 1,000 kilometers in order for this probability to become maximum. And so that's how far we have to send the neutrinos from their source of detection in order to study this problem. Now, there's also another thing, which is interesting, is that if we have three neutrinos, there's actually another degree of freedom which allows neutrinos and antineutrinos to have different probabilities. And this is what we call CP violation. And let me talk a little bit about why that is important. But before I get there, I just wanted to say, another thing that we discovered through this is that neutrinos are extremely light. So physicists